Equilibrium. This is kind of a fun topic because this allows us to talk about what are known as forward reactions as well as reverse reactions. Before we get started, let me go ahead and show you a quick example of this. So, when you're chewing gum, you typically think of gum going from a nice little stick form into this gooey, sticky wad of gum. But let's go ahead and watch what we call the reverse reaction. See if we can go in the opposite direction this time. I've got my stick of gum here, and should be able to go ahead and turn that into a stick of gum. In fact, you can even put the wrapper back on and then stick that back in your pocket. So that would be a reversible reaction, right? Going in the opposite direction. So let's go ahead and dig a little deeper into this topic. Alright, so when we're talking about a reaction, it's often helpful to kind of diagram it out. Now, what we're going to do with this reaction diagram is on the y-axis you can see that we have energy, right? So as energy increases, we will go up this direction. And then here on the x-axis we have what's known as the reaction coordinate, or in other words, we're just kind of progressing along in our reaction, going from reactants on the left to products as the reaction progresses. Now, a few things that you should notice here. We do have reactants right here, and notice that they have a certain energy level, right? So this is where the reactants are at energy-wise. Products are down here on the right, and you can also see that in this case they happen to be lower in energy than the reactants are. Now, in order to go from reactants to products, you're going to have to, push uphill a little bit, right? You're going to have to be able to get over this hill. And at some point, you're going to reach what's known as the transition state. So this is where you neither have true reactants or products, but you have something kind of in the middle, where some bonds are just starting to break, other bonds are just starting to form. And so it's kind of tricky, and this transition state doesn't usually last for long because you can go ahead and just roll downhill from this point and turn your transition state into the products, right? Fully break those bonds, fully make new bonds, and so that now you have some products. Now there are a couple of definitions that you should definitely know, and I'm going to go ahead and diagram those out onto the diagram. So the first one is the energy of activation, or E sub A. So what is the energy of activation? It's the difference in energy between the reactants and the transition state. So notice if I were to go and just draw a line from here and here, there we go. Okay, the energy of activation, E sub A, would be this difference right there, E sub A. Alright, so that's the energy of activation right there. This is the hill that you have to push up and over if you want to start the reaction. And every reaction has an activation energy, right? If you want to start a campfire, you have to light a match to get it going, right? If you want to, do pretty much anything, you have to have some energy. Now, many times the reaction takes place at room temperature because the energy of activation is so small that you can reach the transition state just by the ambient temperature in the room. But sometimes it takes a lot of heat, pressure, and so forth to really get things to react. Think of like your engine, right? You have a lot of energy stored in your gasoline, but in order to get that started, you have to actually ignite the fuel with the spark plugs and so forth, and get things moving. Now the other thing that we should know about would be the enthalpy change, or delta H. So I'm going to go ahead and change colors here. And delta H, the enthalpy change, is the difference in energy between the reactants and the products. So I'm going to go ahead and put some dots here and some dots here, and you can see the difference between reactants and products. That is delta H. Okay. Now, what this means is this is the amount of heat that's either generated or absorbed by a reaction. Okay, so in this case, we're generating a lot of heat because our reactants were very high in energy. Our products are relatively low in energy, and so therefore that excess energy that was stored has to be released out into the environment. Right? So this would be like a campfire where you're producing heat. So once you get up and over the hill, now you're going to produce a whole lot of heat in the process. Just a few quick notes about the E sub A, or the energy of activation. This is, again, the minimum amount of energy necessary to actually jumpstart the reaction, to get it going. And then once it's going, then it usually continues to progress. Now, it makes sense that if that energy of activation is really high, if it takes a lot of energy to get things going, the reaction will be slow because it's going to take a long time to build up enough energy to get up and over that hill, right? It's like my kids and I just ran a 5K, last week, and it was pretty crazy, right? My first one, and I don't know if I've ever actually run that far ever in my life, which is pretty pathetic, but there's a pretty big hill in the middle of it, and so it takes a while to kind of keep getting up enough steam to get up and over that hill. And we did it, but it took some energy. Now, if the energy of activation is low, this is like just going up over like a little tiny rise. It's quick and easy, it doesn't take much effort, and so therefore the reaction will progress quickly because it doesn't take much energy to get up and over that. Now, we can actually look at the reaction diagram and figure out whether a reaction is exothermic and produces heat, or whether it's endothermic and requires heat or absorbs heat. So let's go ahead and take a look at this. You can see that in this case, the difference between the energy of the reactants and the energy of the products is here. This is delta H. And in this case, oops, it's kind of a lousy delta H. Let's try that again. In this case, we're going to say that delta H is actually negative, okay? Because we're dropping down. We're going from here up at the reactants down to where the products are. So that would be a negative delta H. We're going to say that that's an exothermic reaction. Heat is being generated by the reaction. What would an endothermic reaction look like? Well, it would look something like this. So in this case here, we have reactants way down here at a lower energy, products way up here at a much higher energy. And so therefore, delta H here is going to be defined as a positive value. Okay, I always think of this that you have to add energy to it to get to the products, because you're from here to here you're going up, right? You have to put energy in, kind of store it up into the products. So that would be an endothermic reaction. So you should be able to look at it and see if reactants are higher than products, it's exothermic. If reactants are lower than products, it's an endothermic reaction. Now, if I want to speed up a reaction, let's say it's moving too slow, what can I do to actually increase the rate? Well, a couple of things I can actually do. I can increase the concentration of the reactants, which makes sense, right? If I'm trying to get a campfire going and it's taking a while and it's just not burning very fast, I know that fire needs oxygen in order to keep going, right, for this chemical reaction to take place. So I could go ahead and fan it and get more oxygen into it. Or I could even get a tank of pure oxygen if I wanted to live dangerously and blow that onto there, and then it would react very, very quickly, right? So I could increase the concentration of the reactants. I could also increase the temperature, right? I could go ahead and throw on a few more matches onto this pile of firewood, and by increasing the temperature, I'm going to cause those molecules to vibrate faster, and therefore have enough activation energy to get up over that hill and to proceed with the reaction. And then the third thing I could do is I could actually add a catalyst to the reaction. And I'm going to talk a little bit more about what a catalyst is and why it speeds up a chemical reaction. So what is a catalyst? Well, a catalyst is something that's actually going to change the reaction pathway. If you look over here on the right-hand side on this diagram, you can see the uncatalyzed reaction with this large hill, this big activation energy we have to go over. And then we have this catalyzed pathway that's kind of like this secret little tunnel that you can see it doesn't take nearly as much energy to get up and over that hill. So that's what a catalyst does for us. So a catalyst is going to be something that speeds up a reaction, right? And it's going to be recovered unchanged at the end of the reaction. So things can stick to it, it can kind of be involved in the reaction, but at the end of the day, you should end up with the exact same stuff, that the exact same catalyst that you began with. It lowers the activation energy, but one thing that I do want to mention is it does not change delta H. remember that delta H is the difference between reactants and products. So notice that in either case, delta H is the exact same, right? So in this case, we have an exothermic reaction because reactants are higher in energy than products. So notice that that doesn't change. It's still an exothermic reaction. Delta H is still the same amount. So what are some examples of catalysts that you might be familiar with? Well, one would be in your car. You have a catalytic converter. And so what does that do? Well, when you burn gasoline, not all of it actually burns. You have some unspent fuel and partially burned fuel that comes out. And in order to pass emissions, you need to kind of clean that up to help burn the remaining fuel so that you don't just get a bunch of crud coming out of your exhaust pipe. And so the catalytic converter is actually has platinum in there, which is why it's so expensive to replace one of those. And which is also why if you go to a big city, you should actually have your catalytic converter welded onto the undercarriage of your car, because sometimes thieves will actually slide under with a hacksaw. In about 2 minutes they can cut that off, and now they have a bunch of platinum. They can go and sell the catalytic converter. And so anyway, what's happening with our catalyst? Well, what happens in our catalytic converter is that unspent fuel comes in, it blows over the platinum, and the platinum will actually kind of grab hold of the unspent fuel, and it forces those molecules to line up just right, so that way it can easily react with the oxygen that's coming in, and therefore it burns, but it burns at a lower activation energy, right? So it's easier for that to react. And now, with lower activation energy, everything burns quickly, and you have nice, relatively clean exhaust. But at the end of the day, you still have platinum, right? You haven't changed your actual catalytic converter. And theoretically, you could keep doing this forever. Now, unfortunately, usually stuff gets in there into your catalytic converter and it kind of gums it up, and it can destroy it at some point, and then you have to replace it, and then it's a couple $1,000s. Another example of a catalyst would be like an enzyme. So enzymes are biological catalysts. So these are proteins that are in your body, and they help to break things down or to speed up a whole bunch of different reactions. Because many of the reactions that take place in your body need a whole lot of energy to actually occur, and so your body would have to run at maybe 150 degrees Fahrenheit or something crazy if you wanted these reactions to actually take place within your body. And that's not going to happen. I mean, you would die of fever, right? And so the enzymes, their job is to go in there, and they help to speed up the reaction. Sometimes they stretch, bonds, or they expose certain bonds, like peptide bonds, so they can be cleaved. Or the enzyme sucrase will actually take a sucrose molecule, which is composed of glucose and fructose, and it will actually, hold the two sugars, the saccharides, into position, and it kind of stretches it just enough that water can come in and cleave what we call the glycosidic bond, and it does so at a very low temperature. And so, and then at the end of the day, the glucose and fructose go floating off into your body, and now, the enzyme is still perfectly fine. Another sucrose molecule can come in, and this can be repeated, as long as you want, right? Now, again, in theory, the protein could last forever, or the enzyme could last forever. In practice, it doesn't, but luckily you make these new ones all the time. You can actually test out some of these enzymes if you want to. Take like a little piece of saltine cracker or a piece of like Wonder Bread and just let it sit on your tongue, just a little tiny piece, let it sit there, and it seems really gross because it's going to get all soggy, but at some point it'll actually taste really, really sweet because the enzymes in your saliva are actually breaking down the starch, turning it into glucose, and your tongue tastes that glucose as being sweet. And so that's how an enzyme actually works. And so extremely important. One of the reasons that you die if you're, if you get a fever that's too high, is that it actually denatures some of those enzymes in your body, and your body simply can't function without them. Now, if we're going to be talking about a chemical reaction, you'll probably notice actually on this last slide that theoretically we could go from reactants down to products, right? Or we could go the opposite direction. We could actually go from products and go up over that hill and turn it back into reactants. There's no reason, that you can't go either way. Roads go both ways, right? You can run either direction on it. So that's what equilibrium is all about. It's a reaction that can proceed in either direction. So kind of like the video I showed you at the beginning. In this case, we can actually take 2 molecules of nitrogen dioxide, and those can actually combine to form 1 molecule of dinitrogen tetroxide. And typically we go from reactants into products, but there's no reason that we couldn't actually go the opposite direction and go from products back into reactants, right? And so this is equilibrium. So this is kind of a fun little picture. When we first moved to New Hampshire, we were going to the beach, and there's this big statue of a shark. And so obviously, what do you do when you see a statue of a shark? You take your 2-week-old baby and you put him inside of it, right? And so we went ahead and did that. And it's kind of funny, and why do I put this on a page about equilibrium? Well, when you think about a baby going into a shark's mouth, you think of it as a one-way trip, right? The baby goes in and it never comes back out. But luckily, this was a reversible reaction, in which case the baby was able to come back out. You can see how happy he is. And anyway, a little random, but hopefully kind of amusing, at least for me. So we're going to define the forward reaction as going from reactants into products, so going from left to right. And then we're going to define the reverse reaction as going the opposite direction. So if I say in the reverse reaction, you know that you're going from products back into reactants. All right, just a quick definition there. Now, at some point, you're going to reach what's known as equilibrium, where the rates are both occurring, right? You're going from reactants into products, but you're also going from products into reactants. So we're still going both directions, but the rates are equal, and so therefore there's no net change in your overall level of reactants versus products, because you're switching back and forth but going at the same rate. So there's no net change. And again, this is like backwash, right? Stuff goes in, stuff goes out at the same rate, and so there's no net change in the water level in your cup. Now, once you have a system, a chemical system that's at equilibrium, right, where the rates of forward and reverse are equal, you can actually kind of stress out this system. You can do something to it to kind of upset the nice delicate balance there. And Le Châtelier's principle says that the system will actually shift either to the forward or to the reverse reaction. It'll shift in whichever direction helps to relieve that stress. This is the same type of thing that we naturally do as humans, right? If you're under a lot of stress and you've got homework to do, you've got this big paper to write, you have dishes and laundry, and then your buddy needs you to help them move, and you have all these pressures on you, you're going to do something to relieve that stress, right? It could be that you suddenly hurry and try to get your laundry done, or maybe you pay somebody to do your dishes for you or something. Maybe you just go out and eat half a pound of bacon bits. I don't know, whatever floats your boat, whatever helps you to feel a little stress relief is what we naturally do. Chemical systems will do the same thing. They'll shift in order to minimize that stress. So the question is, how in the world do you stress out a chemical system? Well, there are 3 things you can do. You can change a concentration of either a reactant or a product. You could change the temperature, either raising it or lowering it. That'll stress out a system. Or you can actually change the pressure. So changing concentration, temperature, or pressure. Let's see how each of those affect a chemical system. So here's a chemical reaction. This is carbon monoxide, and I can actually burn that with oxygen to make carbon dioxide gas. All right, so this is a reversible reaction. It could go in either direction. And let's say that I decide to upset this system. It's at equilibrium. Everything's, like the 2 rates are equal. It's a nice delicate balance, and I'm going to go ahead and upset this. So what am I going to do? How can I upset the system? Well, I could go ahead and add in a bunch of reactant. Okay. Well, what happens when I add in a reactant, either some more carbon monoxide or some more oxygen? Well, the system's going to shift, but which direction will it shift? Well, this is how I always think of it. I always think of it as landscaping, right? So you have a nice, flat lawn outside, right? Hopefully, and so you want a nice equal, lawn. Looks like a putting green or something. But unfortunately, sometimes things happen, right? So let's say that one morning you wake up and you suddenly have this big mountain of dirt on the left-hand side of your lawn. What are you going to do? Well, let's imagine that you can't, haul it away or anything. It has to stay in your yard. So what I would do personally is I would take some of that dirt and I would shift it over to the right. Okay, so if it's piled up on the left-hand side of my lawn, I'm going to shift it to the right, because by doing that, it's going to help to kind of level everything out, right? So now I have a nice level lawn again, and everybody's happy. Well, it turns out that you can do this exact same thing in a chemical reaction. So you can think of this arrow as kind of being the dividing line down your lawn, all right? And in this case, I just added a reactant, so I added something on this side. So what do I do to my lawn? Well, I'm going to go ahead and shift dirt to this side to kind of balance it out, right? And so it turns out that we would say that in this case, the reaction shifts to the right, or it shifts towards the forward reaction, right? And that's literally what happens in this reaction. Now, what would happen if I added a product? So again, here's my dividing line. I just added a big mountain of product over here. Which way will it shift? Well, it's going to shift to the left, because that way it'll even things out again. So it shifts to the left, or it shifts in the reverse direction. Now, besides adding something, I could also remove something, right? What if I removed a bunch of oxygen? So I have this nice even lawn, and then I just dug this big hole over here. So there's this big gaping hole where the oxygen used to be. What can I do? Well, I could actually shift some dirt in, towards the left to kind of fill in this hole, right? And so that's what will happen, is that this reaction will shift to the left or shift in the reverse direction in order to minimize the stress, in order to kind of fill in that hole. So what would happen if I removed some of the product? Well, now the hole's over here. Naturally, it's going to shift to the right to kind of fill in that hole. All right. So, some books will actually have tables of like, if you add a reactant, it will shift to the right. If you add a product, it shifts to the left. If you remove a reactant or remove a product, it'll shift this direction. And some people like to memorize that, and that's totally fine if that's your thing. I always just think of it as this, landscaping thing, and kind of, this mental picture allows me to visualize which direction it will shift. So we've discussed what happens if you change a concentration of a reactant or a product. What happens if you change the temperature? Well, it depends on whether you have an exothermic or an endothermic reaction. Remember that exothermic heat is exiting the system, right? It's being produced. This is like a campfire or Bunsen burner. So in this case, I'm actually going to write in heat as though it were a product, right? So now, technically that, I can't do that. It's not part of a balanced equation or anything. But I can go ahead and just pretend that it's a product, because in this case, I'm actually, producing heat. So along with the ammonia, the NH3 that I'm producing, I'm also making a lot of heat. And now that I've done that, now it's just like before. All right. If I increase the temperature, that means that I'm adding a bunch of heat, right? That makes sense. So increasing temperature is adding heat. Heat's over here on the right-hand side. So if I increase the temperature, I just added a big mountain of dirt. Which way will it shift? Shift to the left. Okay, simple enough. Oops. Now what would happen? I should write that heat back out there. Okay. Now what would happen to this reaction if I removed the heat, right? If I decrease the temperature? Well, now there's a big gaping hole over here, so I have to shift to the right. So if I decrease the temperature of this reaction, it will shift in the forward direction, or shift to the right, in order to kind of fill in that gap. Now notice that heat is over here as a product because this is an exothermic reaction. If I told you that this were an endothermic reaction, then heat would have to be over here on the left-hand side. It would be a reactant, and then we would just do the opposite, right? If I increase the temperature, I'd be putting a mountain over here because that's where the heat is. So it really depends on whether it's an exothermic or endothermic reaction where you put heat, and then it's just a matter of landscaping again, right? Now, one other thing I should mention is that remember that I could tell you it's exothermic, or I just could tell you that I'm just going to make up a number here, but I could tell you that this reaction has a delta H of negative 523 joules per mole, or something like that, right? And then you would say, oh, look, it's a negative delta H. Therefore, this must be an exothermic reaction. And then you could proceed as usual. If I told you that it had a delta H of positive 152 kilojoules per mole or something like that, then you'd say, oh, that's a positive value. This must be an endothermic reaction. And then you could figure it out from there, right? So just be aware that I could tell you it's exothermic or endothermic, or I could just give you the value for delta H. Now, what's the last thing that we could change? We could actually change the pressure. Now, when you're changing the pressure, one thing I want to note is that we only care about gases, all right? Because remember that gases are affected by pressure. Solids and liquids and aqueous solutions are not affected by pressure at all, okay? So we care about gases in this case, and that'll become apparent in just a minute. All right, so when you're changing the pressure, what are you really doing? Well, think of a balloon. You have this balloon with a bunch of, this chemical reaction going on, a bunch of different chemicals in there of gases, and when you squeeze on the balloon, you're increasing the pressure, right? So you're increasing the pressure as you squeeze on this balloon, and the balloon's getting smaller, so you're decreasing the volume. You have less space. And have you ever moved from a house into an apartment, right? Well, if you have, you'll notice that the very first thing you do is you got to get rid of some stuff, right? Because you're like, wow, we have a lot of junk, and there's just not enough space for it. So you hold a garage sale or whatever to try to get rid of some of that stuff. A chemical reaction that's at equilibrium will actually do the same thing. It'll actually shift to whichever side has less stuff when you increase the pressure, because by increasing the pressure, you have less space. Less space means, hey, you got to go to the side that has less stuff. And by less stuff, I mean fewer moles of gas. All right. So again, we care about gases. So let's go ahead and look at this reaction. Notice that on the reactant side, I have 2 moles of gas, right? So 2 moles of gas. All right. So on the other side of this reaction arrow, I have the N2O4. There's no number written, so it's implied that it's a 1. So I have 1 mole of gas on this side. So if I increase the pressure, which way will this shift? Well, it's going to shift to the side that has less stuff, right? This side has less stuff, so this reaction will actually shift to the right. What if I were to decrease the pressure? Well, decreasing the pressure means that I'm kind of releasing the pressure on that balloon. The balloon's going to get bigger, right? Now I have more space. And if you've ever moved from an apartment, a tiny apartment, into a big house, first thing you do is you walk through and your wife says, wow, we got to get more furniture. Look at all this space. We got to fill it up. And so if you decrease the pressure, then you're increasing the volume, and so you will actually shift to the side that has more moles of stuff. And by more moles of stuff, I mean more gas, more moles of gas. So in this case, the left-hand side, the reactant side, has 2 moles of gas versus 1 on the other. So the reaction will actually shift to the left in order to go to the side with more moles of gas. Now again, if there were liquids, solids, or aqueous solutions in here, I totally ignore those. That has absolutely no effect. I would only be looking for how many moles of gas I have on either side of the reaction arrow. So let's go ahead and finish up by practicing on one of these. So first off, I'm going to tell you that this is an endothermic reaction. All right, so if it's endothermic, should heat be a reactant or a product? Well, it's not producing heat, so it can't be a product. I'm actually going to treat it as a reactant because I have to add heat to this reaction to get it going, right? Heat's going to be sucked up into this reaction. So I'm going to go ahead and put heat here. Or I could have told you that this has a a positive delta H, in which case it would also be endothermic, right? Okay, so here's my reaction. Now, let's go ahead and try a couple of different scenarios and see which way it would shift. Okay, first off, let's say that I add a bunch of hydrogen gas to this. So here's my hydrogen. So if I'm adding it, I have to add it over here on this side. So which way will it shift if I add hydrogen gas? It's going to shift to the left. Okay, so far so good. Now, what would happen if I add a bunch of oxygen gas? Well, here's my oxygen. It's on this side of the reaction. It will shift to this side. It'll shift to the left. What would happen if I remove some water? Well, here's my water. If I'm removing it, now there's a big pit here. So the reaction will shift to the left yet again in order to fill in that gap. What if I increase the temperature of this reaction? Well, increasing the temperature means increasing the heat, adding heat to it. Heat is right here. So when I add heat, I put a big mountain over here on this side. It's going to shift to the right this time in order to try to maintain equilibrium. If I remove heat, if I lower the temperature, it'll shift in the opposite direction. It'll shift to the left to try to fill in that gap. All right, and what happens if I change the pressure? Well, if I'm going to be worried about changing pressure, I need to look at the moles of gas. So on the left-hand side, I have 2 moles of gas. On the right-hand side, I have 2 moles of gas here and 1 mole of gas here, so a grand total of 3 moles of gas. So, what if I increase the pressure? So if I increase pressure, which way will it shift? Well, it's going to shift to the side that has less stuff, right? Because I'm squeezing this down. I'm increasing the pressure, squeezing the balloon. It's going to shift to the left to try to get to the side that has fewer moles of gas, in this case 2 moles of gas versus 3. What if I decrease the pressure? Well, by decreasing the pressure, I am kind of releasing the pressure on that balloon, right? And the balloon's going to expand and get bigger. So now it has more space. It's going to shift to the side with more stuff, which is the right-hand side. It'll shift to the right because there are 3 moles of gas on the right. Okay. Now, one more thing. What would happen if I added a catalyst to this reaction? So if I add a catalyst, which way will it shift? Well, it turns out this is a trick question. Let me show you why. Adding a catalyst will have no effect, right? There'll be no change on the equilibrium. It will not shift to the right or to the left. It will speed up the reaction, and so the reaction will achieve equilibrium more quickly, but it won't actually change the equilibrium. It won't shift it either way. So let me show you why. I'm going to go ahead and draw out a quick energy diagram here. So let's say that this is my reaction. Okay, here are my reactants, here are my products. This isn't very pretty, but you get the picture. All right, so what's happening when I add a catalyst? Well, by adding a catalyst, I give it a new pathway. So maybe this is my new pathway, right? So notice that it's easy. It's easier for me to go from reactants. Oops, 1 second. Try to shift to a little highlighter here. So notice that it's easier to get up and over this hill, right? It doesn't take nearly as much energy. But at the same time, it also makes it easier to go back up over this hill. So it lowers the activation energy, but it lowers the activation energy in either direction. And that's the critical point. And that's why adding a catalyst will have no effect on a chemical reaction, or it will have no effect on the equilibrium. It will not shift it in either direction. It'll speed up the reaction, so it'll achieve equilibrium more quickly, but it won't change the where that equilibrium lies. All right, so that is it for our discussion on equilibrium.